Next 3 lessons are going to be using different kinds of reference values. So the good news is, unlike stoichiometry yesterday, you have to be told you're going to be told, like it'll be very obvious in the question what you're actually doing. So today, the questions will say using bond energies. So on page 307, there is a reference chart with bond energies. If it is a weird multiple bond, it'll be on page 308. But most of them are actually on 307 as well. So when you are writing the test or the quiz, then you will have to be given these bond energies, okay? So we call it an average bond energy. That's how the values are reported, because it is still it's still weird to think about, or it's still sort of, there's still a lot going on in a reaction, not just straight up breaking the bonds and making new ones. There's also a consideration about what the temperature is of the reaction. Has it already been, is it gaseous? Is it almost at melting, at condensation point when it's going to turn into a liquid? So there are other things to consider in a reaction. So it is reported as an average. Not that really, you're just going to use the reference values, but if you are curious of why it says average and not just bond energy, that's why. So even when, I was helping somebody in biology and they had talked about Gibbs free energy. So even when you do enthalpy change, calculating the chaos in a reaction or the entropy affects sometimes how much energy is released or absorbed in a reaction. So that we're really just scratching the surface of thermochemistry. If you continue with biochemistry or chemistry in university, then you'll probably have to take an entire course on thermochemistry after you have taken calculus. So it's like a second or third year course, because you need quite a bit more math, as well as quite a bit more chemistry knowledge in order to really break down what's happening. Okay? So we are going to calculate the enthalpy change for a reaction using reference values. We're going to do 2 examples. One of the questions is what, I said yesterday, is called a formation equation, where you have a compound made from its elements. So those questions aren't so bad. When you have a reaction, like combustion's a common question, then you have to consider in a little bit more detail, what is the Lewis structure of the compounds? How is that going to influence what kind of bonds there are? Okay, so what in our note, I have drawn in the Lewis structure for you. So and if you take a look at the textbook, some of them are in there as well. Common ones like oxygen is a double bond, CO2 is 2 double bonds, for example, which changes what kind of bond energy you're going to use. So then on the test, etc., assessments, then I'll give you those Lewis structures, okay? But when you do the homework, and if you get to something that doesn't have a Lewis structure in the question, what I would do is just Google it, because I'm not going to make you draw the Lewis structures and then try to do the math, okay? So we are going to calculate the reference values for bond energy, looking at what is the bonds inside the reactants, and then what are the bonds being made in the products. So the equation here is going to be how we are going to find the overall enthalpy change for the reaction. So we are looking at the energy in the bonds broken minus the energy in the bonds formed. Whenever we use a reference value, it's going to, like a chart from the textbook or something like that, then the units are going to be kilojoules per mole. So when the mole isn't 1, then you have to take into account the coefficient. So what we're going to see, I'm going to show all of my units because eventually we're going to cancel out the moles. So the units, just like other cases where you have the enthalpy change for the reaction, the units will just be kilojoules. Okay, so here it says in words here what I just said. So if you have a simple formation equation, then generally speaking, the questions are a little bit more straightforward. If you use bond energies to calculate delta H for a more complicated reaction, we have to take a look at the Lewis structure. Okay, so actually this one is just a formation equation. We have hydrogen gas and chlorine gas make hydrogen chloride gas or hydrochloric acid. What I'm going to do, you can do this question without actually doing the Lewis structures, but let's draw the structures when it's easy so that when it's harder, you're able to deal with it a little bit better. So when you have hydrogen gas, how many valence electrons does hydrogen have? 1. So there are 2 hydrogens, which means 1 bond. If you have chlorine, what's chlorine's charge, or what's it going to do when it reacts? Yes. Good. Gain 1 electron. So it's also 1. So then when you have them in a diatomic molecule, it's going to be single. And when you have a chloride or a chlorine gas, then it's going to be single as well. And then when you have the compound over here, it will also be a single bond. So this is a very, very simple type of question. And then we'll do a combustion reaction, which is a little bit more involved. Okay, so look at, if you have a textbook or somebody in your posse has a textbook, you turn to page 307. Okay, so when you do the homework, you have to look them up. In an assessment question, they will be right in the assessment question. So what happens is when you look up the reference values, they are all positive. And the reason is they are reported in this way because you're thinking about how much energy is stored in that bond, how much energy does it take for it to be broken. And then when we use the relationship, the moles times bond energy in the reactants minus the moles times bond energy in the products, then because it's subtracting, then if the overall change is going to be exothermic, which is very, very common, then the math itself will work out, okay? So all the values here are listed as positive. If you wrote ClH, so if you look at 307, it says HCl is 427 kilojoules per mole. If you happen to write this like this, ClH, that doesn't matter. It doesn't matter what element you put first in the bond and what element you put second. It's more about are the bonds single or multiple, and how many of them are there in the molecule. So how many hydrogen bonds do we have in H2? We only have 1. How many chlorine bonds do we have? Only one. How many HCl bonds? Only one. So what I like to do is take a look at the bonds themselves, and then when I go do the formula, that's when I'm going to use the valence coefficients, because then you can cancel out and use dimensional analysis and figure out the units for your answer. Okay? You don't have to do it that way. Your textbook uses, if you're a textbook reader, they use this chart. You can do it in a chart. It just depends what works for you. Okay, so I'm going to write the reference value right underneath the bond. So HH is 432 kilojoules per mole. It does say they have simplified the chart. So it says none of these numbers have units. It says in the top here the units are kilojoules per mole. Okay, so just watch out for that. And then ClCl is, there it is, 239. And then HCl is 427. Yes. I'm going to do that when we use the formula so that I can cancel the units out. But that is a possibility. You sort of have to decide what you like better. Okay, so now I'm going to use this relationship. So it is reactants minus products, and we have to take into account the coefficient or the moles. What does this symbol mean? I guess I didn't talk about that. Yes. Like the sum? Yeah, the sum. Okay, so we're going to add them together, all the reactants together, subtract all the products together. So please don't feel like you have to do that all as one step. There is definitely a way to punch that into your calculator. However, it is easy to make errors. Okay, so you do not need to try to do that all as one step. We can show as much work as we possibly can. That's okay. Okay, so like Ilya said, I have to take into account this coefficient, and so I'm going to do that in the formula so that I can cross out the moles, because there aren't just one mole there, and then my answer will be in kilojoules, which is what it should be. Okay? Okay, so what I'm going to do right now in our examples, I'm going to, even though there is nothing written here, so what number is understood there? 1. So if you multiply or divide by 1, does that change your answer mathematically? No, but it is going to help with dimensional analysis. Eventually, when you do these questions, if you're like, I'm not writing the 1, that you do you, okay? You decide. When you add, it doesn't matter the order. I'm just going to go in order of the reactants. So technically, according to dimensional analysis, when you multiply by the coefficient, then the mole cancels out. And then you are left with just kilojoules, okay? So generally speaking, like when we do Hess's law next week, when you have a like a reference situation, an overall reaction, then you want to be able to apply it to any reaction, which means it can't just be, it's not always coefficients of 1 all the time. So this is a good way to check and make sure you've got the right units, okay? So it's up to you how much work you would like to show. Certainly with a question as simple as this, then maybe you would like to put this in your calculator just like this. But again, that is not a requirement. I am not expecting you to take shortcuts if that's not what you enjoy. So 432 times 1, which is 432, plus 1 times 239, which is 239, gives 611, minus 2 times 427 is 854. And it does make sense that our answer is negative. Yes. I get 671. 432 plus 239. That's a 9. Did I? Sorry. Oh, sorry. No, that's good. Call me out. Okay, so the next question, it definitely requires a little bit more consideration of what's happening with the Lewis structure, because what happens now is there are more than one bond of the same type within a molecule. So what happens is when you go to do these questions, your textbook, is a bit ruthless, because it's like, okay, we already studied organic. A student should know what ethyne is. You should be able to draw it, but I get it. It was a long time ago. Maybe you hated organic and pushed it out of your brain. So when I give you a question, I will write it like this so that you can see what the Lewis structure is. When you go to do the question, if you are stressed about what the formula is, like for example, one of the questions wants you to do N2H2. If you don't want to have to draw that Lewis structure, I would just Google it before you start, okay? Or take a look at the solutions, and it will be drawn in there. The good news is at least 2 of the homework questions are a combustion. So every time you see O2, it's going to look like this. Every time you see CO2, it's going to look like this, and water always looks like this, okay? So you can also use this as reference. So YNE is triple bonds. That's why there's a triple bond. So when you have a question like this, there is coefficients, and you're going to have to count the number of bonds. So again, you can use a chart like your textbook does, or you can write down the information and take a look at how many bonds there are, and then wait till you get to the formula and use the coefficients there like we just did, okay? So it is kind of up to you what you would like to do. So in C2H2, so I am not going to worry about these coefficients right now, okay? In C2H2, there is, I guess, a C triple bond, C bond. And there are 2 CH bonds. 1, 2. So C triple bond C is 839. And CH is 413 times 2, because there are 2 of them. You can even do it like this. Oxygen, because my sheet's already red, I don't know if yours is only black and white, sorry. So oxygen, when in an oxygen molecule, there's only one OO bond, that's double. So this is just going to be 495 kJ per mole. But then when you get to CO2, now there is CO and CO. There are 2 of them. And of course, carbon dioxide, which is in every complete combustion reaction, is the exception. So if you see at the bottom of the chart, it says there's a star, C double bond O in CO2 is 799 kilojoules. And same thing with water. There are 2 OHs. And again, if you write HO, that doesn't matter. Oh, sorry, I didn't write out. OH is 467. When we do Hess's Law and standard enthalpies of formation next week, it's a much more straightforward process, and you're going to say to yourselves and maybe to me, why did we ever do this? This is insane. Because there is a lot of possibility to forget a bond, which can be very annoying to a student, okay? So the more you write down and the more work you show, then hopefully you will make less mistakes, okay? So it's up to you. Again, you can go now right into the formula for the overall reaction, but you would have to consider like the 839, 2 times 413, the bonds inside CH2, plus the bonds inside oxygen, plus the coefficients, then subtract the, so there is more work you can show in this step if you like, so that hopefully then you won't make as many mistakes, okay? Okay, so I'm gonna write down what the math I have so far, what the answer is. So 839 plus 2 times 413 is 1665. I guess I put equal sign, sorry. Oxygen is fine. There was only one type of bond. 2 times 799 is 1598. 2 times 467 is 934. And what happens is every single time you have CO2, it's going to be 1598. Every single time you have H2O, it's going to be 934. And so when you might be like, how come these numbers are always the same? But it's because we're using the reference value. Those bonds we're going to say are always the same. We've already taken the average. So water is a really common reactant and product. So you might see this sort of situation often, okay? Not that you have to memorize it, but you might be like, wait a minute, I've seen this before, because we're going to use this all the time. Same thing when we get to enthalpies of formation. Some people are like, oh, I have carbon dioxide memorized, I have water memorized, because so many of the questions include that as part of their chemical reaction, okay? So now I'm ready to do this relationship. I have figured out in each reactant and in each product how much energy is inside the bonds. Now I can take into consideration what's happening in this reaction. What is the coefficient? So I have 2 times the amount of one bond energy if it was just one molecule, but I'm going to now take into account the coefficient. That's supposed to be a minus, sorry. So 2, again, I'm going to write mole so that I can show dimensional analysis. So ethine is 1665 because I've taken into account the 1 triple bond and the 2 CH bonds, plus, sorry, this is terrible handwriting. Plus 5 oxygen, so 5 times 495. Minus the 2 products. So I have 4 times the bond energy inside of a, and I'm running out of room, so I'm going to write it on the second line. I apologize. 4 times the bond energy inside of a, what's that called? Carbon dioxide. And 2 times 934. So I'll do 2 times, actually, and you like to do dimensional analysis, All the moles cancel. Actually, I'll wait. I forgot. It's got to be in the video. Is it okay if I switch? Okay, so I'm going to do 2 times 1665 plus 5 times 495. I'll write that down, and then minus, and then I'll do 4 times 1598 and plus 2 times 934. The moles have been canceled out because we multiplied by the coefficient. Negative 2,445 kilojoules. So should a combustion reaction be negative? Yes, those give off energy. Should combustion reactions, should it be a lot of kilojoules? Probably yes. What do we use, what can we use ethine or ethene in? Does anyone know? What? Yeah, like in a, or what's it called? Welder's torch. So obviously those things are very, very, very high energy. You would not burn ethine in your car, okay? Not safely anyways.